Hey guys, in this video we're going to be stepping it up a notch with the indefinite integrals. We're going to be doing some more advanced ones. So hopefully you've got a grasp on the basic ones here. For example, like if we were to just pick out, say, number 3, and just a little review on how to do that. When you have just a polynomial for an indefinite integral, you're essentially just going to do the opposite of the power rule on all these, which is to say that you add a power and then you divide by that. So this first one would be 10 divided by -2 times t to the -2, because we're adding 1 to the -3. And then it would be plus 12 divided by -8 t to the -8 plus 4 divided by 4 t to the 4th plus c. Don't forget that plus c on all these. So we've added a power and then we're divided by it, and then we just simplify -5t to the -2 minus 3/2 t to the -8 plus just be 1, so it'll just be t to the 4th plus c. So that is just a basic indefinite integral of a polynomial. So again, hopefully you've got those down pretty well. We are going to, like I said, step it up a notch. You've also done some where you have radicals, so let's just do one of those real quick. Let's do a harder one here, like number 7. The first step, if you have a radical, is going to be to rewrite the power as an exponent. So remember, on these, the top is the power, the bottom is the root. So all of these, well, this one at least has imaginary 2 out there. So this would be x to the 7/2, our integral out here still. So x to the 7/2 minus 7x to the 5/6 plus 17 x to the 10/3 dx. And really what we're actually doing on all these, we're kind of just doing this in our head, but I do want to show you this, is we're splitting this up into a bunch of different separate integrals. So this is really the integral of x to the 7/2 dx minus, and then the 7 actually pulls in front of the integral, 7 integral of x to the 5/6 dx, and then plus 17 integral x to the 10/3 dx. So this is really what we're doing on each of these. We're breaking each of the separate terms into a different integral. And notice how I even wrote the dx on all of those. That just tells us we're integrating with respect to x on all of these different integrals. So we split it apart, and we actually do pull the constants out in front. We just kind of do this in our head without thinking about it. But these are properties of indefinite integrals, the same properties that you use when you did derivatives. You just don't think about them after you do them for a while. But it is kind of important to make sure that you know what these properties are. There's some scenarios on the AP test where you're just given sort of values for these integrals, and you've got to apply these properties. So just so you're aware that that's what we're actually doing on these. And then for each individual one, we are then adding and then dividing. It becomes a bit more challenging with these fraction exponents. So like, for instance, this would be x to the, when you add 1 to it, that becomes, you're adding 2/2, so that becomes x to the 9/2. And then you divide by 9/2 minus 7. And you might just want to keep that 7 out there for now. And this would be x to the, we add 6/6, so it would be 11/6 divided by 11/6 plus 17 x to the 13/3 divided by 13/3 plus c. And then when we simplify all these, remember that you flip the bottom and multiply. So this becomes 2/9 x to the 9/2 minus, and then since we got a 7 out there, we're really timesing it by 6/11. So that would be like time -42/11 x to the 11/6 plus, and then same with this one, we're flipping and multiplying really by 3/13. So that would be 51/13 x to the 13/3 plus c. So that should be a half, sorry. So it's kind of crazy as it looks. That is how you'll do these. All right, let's go look at some different scenarios here. So one key note as we progress here is for integrating, which is what we're doing, or anti-differentiating, same word, we're integrating, there is no quotient or product rule. No quotient or product rule. Now, why is this important? Well, if we take a look at some of these harder questions we're going to get to, for instance, this next one, number 9, you don't actually need to use a quotient rule for this, but it looks like you might end up needing to do that, right? At some point, start to think about it like on number 12 or number 13. You might start thinking, well, what's the quotient rule for anti-differentiating or integrating? Well, the unfortunate thing is there is none. It doesn't quite work in reverse the same way differentiating does, where we got these nice, easy rules that we just kind of follow step by step. Fortunately, it doesn't work out that way. Same with the product rule, like on number 10. There is no product rule for this. So we have to get a little bit creative. And like I said, the next video, we're going to be doing something called U substitutions. And there's also another technique called integration by parts, which the more and more complicated integrals you get, the more challenging it does become. We do have ways of finding those integrals, but they're just not as easy as, hey, use the product rule here, hey, use the quotient rule. You got to use some other techniques which require a bit more thinking. So these are possible. Today, we're not going to need any special rules. We're basically just going to be simplifying in some ways, and then that will allow us to use the techniques we already know. So for instance, if we were to jump in and look at number 9, so we don't need any special rules for this. We just need to rewrite this in some different ways. So in number 9, I'm just going to rewrite this integral. Bring all these powers up. So this would just become 7/3 y to the -6th. And this would just become plus y to the -10th, because the 1 would just hang out there, right? And then this one would come up. It would just be -2 y to the -4/3 power dy. So you've got to be aware of how to rewrite these. These are just basic algebra 2 rewriting from rational exponents, negative exponents. You got to know how to do those, and just got to be like second nature for you. So then you would just apply the same rules from here. You could split these integrals apart, add 1, and then divide by it. It would work the same. So for number 10, this one, again, there's no product rule. So our substitute here is, well, to just go ahead and FOIL this out, because we can do that. So if we FOIL this out, we just get 4t squared plus 3t to the third minus 4 minus 3t dt. And then we can just do each of these separately, right? And again, what we're really doing when we're evaluating this is we're splitting these up into separate integrals. So it's really like 4 integral of t squared dt plus 3 integral of t cubed dt minus 4 integral of dt minus 3 integral of t dt. So you're actually doing this on all of them. We just don't actually write it. But then, so this would then be 4/3 t to the third plus 3/4 t to the fourth minus 4t minus 3/2 t squared plus c. So it still works the same. You just got to do some algebra here first. Same with like this next one. You're just going to distribute this. You want to look at this as z to the 1/2. So this would be rewritten as z to the, well, 2 plus 1/2 would be 5/2. Also, this one we want to view as minus 1/4 z to the -1, right? And then when we distribute it in, remember when you multiply, you add the exponent. So that would actually become -1/4 z to the -1/2 power dz. And then you would go ahead and integrate it from there. So this would then be 7/2, z to the 7/2 divided by 7/2 minus z to the positive 1/2. So 1/4 z to the positive 1/2 divided by 1/2. And you just simplify from there. So I'm not going to go through how to do all those, but at least make you aware of how to do that. With something like number 12, where it looks like you might want to do a quotient rule, what you're actually going to do here is you're going to just split this up into a bunch of different terms, applying that denominator to every single term. So this has to get applied to each one of these. You can't just divide it out with a z to the 8th and ignore it for the rest of it. It applies to each and every one of those terms. So what you want to do is write this as z to the 8th over z to the 4th minus 6z to the 5th over z to the 4th plus 4z to the 3rd over z to the 4th minus 2 over z to the 4th dz. And then we'll simplify each of these individually. So we get the integral of just z to the 4th minus 6z plus 4z to the negative 1 minus 2z to the negative 4 dz. So we just subtract the exponents, and then we could go ahead and evaluate it from there. It would be very much the same for number 13, maybe just a little bit more challenging. I would first probably write this one. We are going to split it apart, and again, this has to go to both of these terms. X to the 4th divided by 6x to the, and remember that is 1/2 power, because it's the square root, so it's 1/2 power, minus x to the 1/3 over 6x to the 1/2. So you got to get a little creative with this one. This will, you're still going to subtract the exponents. So it'll end up looking like this, 1/6 x to the, and then you got to do 4 minus 1/2, which that would be 8/2 minus 1/2, so it'd be 7/2 power, minus, in this one, you actually got to get a common denominator. It will be 1/6, and then it will be x to the, convert them to 6, so that would be 2/6 minus 3/6, so that would be the negative 1/6 power dx. And then we would go ahead and differentiate, anti-differentiate from there. So we add 1, so it'll be 1/6 x to the 9/2 divided by 9/2 minus 1/6 x to the, let's see, 5/6 power when you add 1 divided by 5/6 plus c. And then simplifying that, you take the bottom, flip it, so it becomes 2 over 54 x to the 9/2 minus, flip that one and multiply, actually becomes 1/5 x to the 5/6 plus c. And then you could reduce that 1 to 1/27. Okay. So that's just a brief intro on how to do that. Now, something we haven't seen yet is how to do trig functions with integrals, because unfortunately trig functions don't go away. I know they're probably not your favorite, but trig functions are an important part of calculus. So with trig functions, we're basically going to think in reverse. Think in reverse. So instead of thinking, before you thought, well, what's the derivative of sine, right? So now you want to think, what function, when I take the derivative, will give me sine? Now, there isn't actually a function that gives you sine when you take the derivative. If you went and looked at our class page here, and looked at this derivative cheat sheet, hopefully you have the trig functions pretty well memorized. But if you're looking for something that will give you sine, you're basically looking at this column over here and find one that gives you sine. Cosine doesn't give you sine, but it does give you negative sine. So that was close enough. So what we end up doing then is we just throw a negative in front of there. So when we actually split this one up, I'm going to go ahead and write it as separate functions here. The integral of sine of x dx plus 10 integral of cosecant squared of x dx. When we think about, well, what when we differentiate will give us sine, again, nothing doesn't, but cosine gives us minus sine. So the integral of sine is actually going to be minus cosine. Minus cosecant minus cosine of x. And how we can figure that out is if we were to go in reverse, so if I were to go back up to there and I were to take the derivative of minus cosine x, well, the derivative of cosine is minus sine, so I'd get minus sine of basically minus sine of x, right? Because I have the negative and the derivative of cosine is minus sine. So minus sine of x, which is sine of x. All right, so you have to think in reverse, which can be a little bit challenging, but how I would suggest you doing it is hopefully you have at least these major 6 ones memorized. So you should have derivative of sine, cosine, tan, secant, cosecant, and cotangent. Those should be memorized. You probably don't have these inverse ones memorized. We haven't really worked a lot with those at this point, but I will show you a situation where you need to use those today. But you need to have those 6 major trig functions memorized. I did also post on the class page integral cheat sheet as well. So this integrals cheat sheet, which has some techniques we'll be talking about pretty soon. It talks about how here you can split them up, basic things we've done. As far as the trig functions here, you'll see the integrals of trig functions. It uses a u in there instead of an x, but same deal. And here you'll see like the integral of cosine of u is sine of u. Integral of sine of u is minus cosine of u. So it's just basically staying the opposite. So if you actually did want to look up the derivative or integral of sine of x, you can see that it is minus cosine of x. But don't get too comfortable using this cheat sheet because you won't have it on the AP exam, but it is there for you to help you if you need it for right now. Okay. So we got the first part there. For the second one, notice how I pulled that 10 in front. It is helpful to look at it that way so you can kind of just focus in on, you're just trying to figure out what, when you take the derivative, will give you cosecant squared. So if you think back to your derivatives, and I'm going to pull up your derivative cheat sheet here, you need to get a cosecant squared out of it. So basically you're going to be looking at this right side of the column over here, and there you do see a cosecant squared. So the derivative of cotangent is minus cosecant. Now we just want cosecant, so all we have to do is throw a negative in front of there. But this is actually going to be minus 10 cotangent x plus c. And that is actually going to be our answer. And again, the way that you can check this is if you were to take the derivative of this, well, the derivative of cotangent is minus cosecant squared, so you have negative 10 times minus cosecant squared, x minus minus becomes a plus, so it becomes 10 cosecant squared x, which is what we started with there, right? So this is going to be a little bit challenging thinking in reverse, but you can always check your answer by taking the derivative and seeing if you get the original problem. So I'll go through a few more of these here. Number 15 here. Again, I would advise breaking this up into 2 integral cosine of w dw minus integral. Now this secant tangent, notice how they're multiplied. That's okay. You don't need a product rule because if you think back when we did derivatives of trig functions, there was one where it was secant x tangent x. So with this, we're just going to leave secant w tan w dw. All right. So let's go ahead and think about this one. So we want to think, well, what when we take the derivative gives us cosine? Well, remember how sine and cosine are opposites. The derivative of sine is cosine. So this is just going to be 2 sine of w, right? Because the derivative of sine is cosine. Gives us back there. Minus, and then think what derivative when we, or what function when we take the derivative gives us secant x tangent x or secant w tangent w. And that is secant. Derivative of secant x is secant x tangent x, or in this case, secant w plus c. So you go back and look again. The derivative of secant here is secant x tan x. So the derivative of secant of w would be secant w tan w. All right, and let's go ahead and do this other trig function here. It can be a bit tricky. This one does have a multiplication, so what you're going to do first is go ahead and distribute that one for number 16. And I'm going to write this as 12 integral of, this is d theta, plus All right, and then we're going to have, for this one, it's going to be cosecant theta sine theta. So integral of cosecant theta sine theta d theta plus integral cosecant theta times cosecant theta. Now, before we do anything with this, we actually want to simplify this some. All right, we're just going to keep this one as 12 integral of d theta plus, now this looks a little bit confusing because there's nothing that when we differentiate, we're going to get a cosecant theta sine theta. So you got to do a little bit of tricks here. Remember that the cosecant is actually 1 over sine, right? So if we just replace it with 1 over sine, well, we'd actually see it says 1 over sine times sine. And those actually would just cancel and leave it with just 1. So we actually end up with just basically 1 d theta. So 1 d theta, essentially, or just d theta with that one. And then plus, well, cosecant times cosecant is cosecant squared. So it's the integral of cosecant squared theta d theta. And then we can go ahead and do this. For the first one, it's just going to be 12. And actually, if we kind of take a step back, you could actually just combine these two. 12 and 1 is 13. So it's just 12. I'll go ahead and just write it as 12 theta plus 1 theta, or just theta. But you could have combined those. And then you think, well, what gives you cosecant squared? If you look back at your table of derivatives, there is a cosecant squared there. That's cotangent, but it's the wrong sign. So we got to throw a minus cotangent theta plus c. So then we get 13 theta minus cotangent theta plus c. And there we go. All right. Well, let's go and look at an E problem. I know you all love E's as well as trig functions. Let's look at 17. All right. So 17, I'm going to go ahead and split it up. I'm going to pull the constant out. So for integral of e to the z plus, and that's just a 15. So 15 integral, I forgot my dz there, integral of dz minus, and then for this one, I'm just going to pull out a 1/6 essentially. So it just is like 1/6 integral of essentially z to the negative 1 dz. So hopefully you're tracking there so far. Again, I just pulled out 1/6 and then I took that z up and made it z to the negative 1 power. Okay, so then for integral of e to the z, well, if you remember in our derivatives, the derivative of e to the x is just e to the x. So the opposite would be true. The integral of e to the z is just, well, e to the z. So this is just going to be 4e to the z plus, this is just 15 dc, so that's 15z minus 1/6. Now here's where you got to do some other thinking back, a lot of reverting back to old stuff today. When we add 1 here and divide, we would get z to the, well, 0 divided by 0. That can't be right because we get undefined, right? So something's amiss here. So what I do want you to think about is if we were to look at this instead of, I know generally we're supposed to write it as a negative exponents, but if we looked at it as 1/6 integral of 1 over z dz, and think back to a derivative that when you take the derivative, you get a 1 over z or 1 over x or something like that. And you might recall that, oops, the natural log function, ln of x, the derivative of that is 1 over x. So I think I might have this. There we go. All right. So to get 1 over z after you take the derivative, turns out it's just actually the natural log of z. Because again, when we took the derivative, I'm going to put my plus z there. If we take the derivative of the natural log of z, it's just going to be 1 over z. So if I were to differentiate this back, I would end up with my original function. So again, just to show you, if I were to take the derivative of this, it would be, well, the derivative of e to the z is just e to the z. So it's 4e to the z plus 15, right? Because the z would just go away. And then it's minus 1/6. And the derivative of the natural log of z is 1 over z, right? So then we get 4e to the z plus 15 minus 1 over 6z. And that's what we had to begin with here. So you can always double check it that way and erase it. All right, and then I want to do number 18 as well real quick. So this one, integral of t to the third dt. Now remember, this one has got to apply to both of these. So this is going to be minus integral e to the negative t over e to the negative t. All right. The next term will actually become a plus because we got a minus, so plus 4, and then it would be integral of 1 over e to the negative t dt when you rewrite that one. So then integrating this would be 1/4 t to the 4th minus, now e to the t over to the e to the t, it would just be 1, put my dt there. So this actually just goes to 1. So it's just 1 dt. So when we take the integral of that, it's just minus t plus 4. And then this one, well, it's e to the negative t. E to the negative t is actually the same thing as just saying e to the t. 1 over e to the negative t is just the same thing as saying e to the positive t. Because remember, when you take something up, you got to add a negative to it. Well, this one's already negative, so that 1 over e to the negative t is actually just e to the positive t. So the integral of that would just then be e to the t plus c. All right, number 19. This one, it doesn't look hard, but the only tricky thing on this one is the integral of that part would be like minus 2, 1 over w dw. And that one, when you take the integral, remember, is just the natural log of w. So it's a little tricky in that one. These last couple here, I might have you try these. We haven't done a lot with the inverse sine and cosine and tangent functions. But if you look at this sheet I gave you a while ago, you'll see these inverse sine, cosine, and tangents. They're not used very often, and they have these formulas for finding the derivatives. And if you look at these here, you can see these look very familiar to what those look like. So for instance, 1 over 1 plus x squared, well, that's actually just inverse tangent. See, it's exactly the same, 1 over 1 plus x squared. So this would just be the inverse tan of x plus, now this one looks just slightly different, but you can tell it's the same as, well, one of these is positive 1 over square root of 1 minus x squared, and one is negative. And so we want the positive one. So that's almost the same as the inverse sine. It's just the only difference is this 12 here. Well, that 12 we could just pull out in front and write it like this. So it's just going to be 12 inverse sine of x for that one. Same with this one down here. It's very similar. You would just pull the 4 in front to do that. So that's how you do those. So I might have you try a couple of those. You are going to need to look at this derivative sheet, or you could look at, I suppose you could look at the integral sheet. But actually, since you're more familiar with the derivatives, I find myself, if you're going to refer to anything, just referring to the derivative sheet and thinking backwards. But feel free to choose whatever you'd like. All right. The last couple problems here, these are actually problems like you did on Delta Math with the initial conditions. So it gives you a derivative, and then it tells you to determine the original function, and it gives you an initial condition here. So I do want to try one of those. They're not difficult. You're just going to take the integral of the function it gives you, integral of f prime of x. So this is just like the when we were going from velocity to position. It's just like that, except it doesn't call it that. Take the integral of this. So that gives you 12 thirds x to the third minus 4 halves x squared plus c. So this would be f of x, right? This would be like our general solution, which we could reduce to 4x third to the third minus 2x squared plus c. So that's our, what we call our general solution. We then can use this initial condition to find what the c is. So if we know that f of negative 3 is 17, we would say that 17 equals 4 times negative 3 to the third minus 2 times negative 3 squared plus c. That would give us 17 equals, see, that would be negative 27 times 4. Let's make sure we do this correctly. So we get negative 108. That becomes 9, so minus 18 plus c. So we end up with, looks like negative 126 plus c. Add that over. So c would be 43, looks like, 143. Yeah, so c is 143. And then so our actual solution, f of x then would be, plug in this c back into here. So f of x would be 4x to the third minus 2x squared plus 143. It would work the same for this E1, just be a little bit more challenging. Same with if you had to do this one, it gives you h double prime of t. So you would just need to do in 2 steps. It gives you an initial condition for, actually, I think it's missing, one of these should be h prime of t, or h prime of 1 or something. So we'll just X this one out for now. We'll just stick with the first one. Let's go ahead and try number 23, end with a bang here. All right, so for this one, this is going to be a little more challenging. We need to take the integral first of 3z to the third plus, and I'm going to go ahead and rewrite this thing. That's going to be 7/2 z to the negative 1/2 minus e to the z dz. All right, integrating this would be 3/4 z to the fourth plus 7/2 z to the positive 1/2 divided by a positive 1/2 minus integral of e to the z is just e to the z plus c. Simplifying this a bit, we get 3/4 z to the fourth. Flip that bottom and multiply. The 2's would actually cancel and gives us just plus 7 z to the 1/2 minus e to the z. And that would be, g of z. That's the general solution. It gives us an initial condition here. G of 1 equals 15 minus e. So that's just saying g of 1, 3/4 times 1 to the fourth plus 7 times 1 to the 1/2 power minus e to the first equals 15 minus e. Oh, sorry, I forgot my plus c there. Plus c equals 15 minus e. So then we need to get the e by itself. Well, we get 3/4 plus 7 minus e plus c equals 15 minus e. Looks kind of crazy here, I know. But what happens here when you add this e over, actually cancels with that e. So those wipe each other out. If we were to combine those, we would get, let's see. Well, if we just subtracted the 7 over, we would get 8. So 3/4 plus c equals 8. Then subtract the 3/4. That would be, well, this is 32/4. So that would be 29/4 would be c. And then so our final answer, g of z equals, we're going to plug this in there, 3/4 z to the fourth plus 7z to the 1/2 minus e to the z plus 29/4. And there we go. All right, so I know some of these take some work. This assignment will probably take you a while, so make sure you plan plenty of time to do it. Don't try to do it at 11 o'clock on the night it's due, because this will take you some time. So good luck, and do reach out to me if you have questions. Thanks, guys.